This is the third and final example of a linear programming problem. So this one is unusual in a couple of different ways. So I'd like to go through this one with you and just try to hit some of the trickier aspects to these problems that you might see as you do some of the exercises for your homework. Okay, so to start out with, let's read the problem and then try to begin with identifying the variables and then going through the rest of our steps. All right, so Elizabeth Lamel takes vitamin pills. Each day she must have at least 16 units of vitamin A, at least 5 units of vitamin B1, and at least 20 units of vitamin C. She can choose between red pills costing 10 cents each that contain 8 units of A, 1 of B1, and 2 of C, and blue pills that cost 20 cents each and contain 2 units of A, 1 of B1, and 7 of C. How many of each pill should she take in order to minimize her cost and yet fulfill her daily requirements? Okay, so notice first of all that this is a minimization problem. We're not trying to maximize anything. Our objective is now to minimize something. Also, we've got quite a few other numbers. In this one, we've got vitamin A and B1 and C, numbers all over the place. So to pick through this information, we'll just take it a step at a time. And we'll begin, as we usually do, with identifying the variables in the problem. All right, so usually this will be the last sentence, and it's going to be phrased as a question. All right, what do you need to find? All right, how many of each pill should she take? All right, so regardless of how many other seeming variables you have in this problem, which look like variables because of the letters A, B, and C, right, we really just have a two-variable problem. We've got an X and a Y. We have how many of each pill. We've got red pills and blue pills. All right, so let's let X be the red and Y be the blue. Right? And I know that we can't have 3 variables or 4 or 5 because we would not be able to graph this problem and we would need to use a different technique. All right, so if we're going to graph this on a coordinate plane, then we just need X's and Y's in order to be able to do that. All right, and then an objective function. So now we're trying to minimize cost. So cost equals, all right, and we know red pills are 10 cents each. And I will do these in terms of cents just so we don't have to deal with decimals. And blue pills are 20 cents each, so 20 times the number of blue pills that she purchases. All right, and that's what we want to minimize. Okay, now the constraints. So if you read through, the first kind of key phrase that we get to that indicates a constraint is at least 16 units of vitamin A. All right, so you might be tempted to say something like A has to be at least 16. All right, but we can't actually do this because if you remember, all of our constraints have to be written in terms of X or Y so that we can graph them. And this A, we don't have A as a variable, we just have X and Y. So we have no way to really express at this point the fact that A is greater than or equal to 16. All right, and then it would be the same for B1 and C. We've got at least 5 units of B1, but no way to express that, but because we don't know how B1 relates to X and Y. All right, and the same issue for C. All right, so here's my suggestion. If you hit a problem like this, hopefully you'll be able to see that this is a little bit different because of not being able to write the constraints directly from the problem. So let's set up a chart to try to help us figure out the relationship between the units of each vitamin and which pills those units are coming from. All right, so I will do red pills and blue pills. I'm going to do a row for each of those. So red is my X, and then blue pills, Y is how many blue pills she takes. All right, and then we'll do a column for each of the vitamins. We've got A, we've got B1, and C. All right, and then at the bottom of each column, let me just kind of record and jot down restrictions or constraints on the units of vitamins. So I know that A must be at least 16 units, so greater than or equal to 16. B1 must be greater than or equal to 5. And C must be at least 20. All right. And then I'll go back and fill in some of these other numbers. Red, I know red pills have, there we go, 8 units of A. Okay, 1 of B1 and 2 of C. And then blue pills have 2 units of A, 1 of B1, and 7 of C. Alright, so right now I've just recorded the amount of units in one pill, one red pill or one blue pill, but I also need to take into account that she could be taking multiple pills. So if she was, for example, to take 3 red pills, then the amount of vitamins she'd actually be getting would be 8 times 3, okay, 8 units for each of the 3 red pills, 3 times the 1 unit of B1, and 3 times the 2 units of C. Alright, so instead of 3, I don't know how many pills she's taking, but I can say that she's taking X pills. So I would go back and multiply each of those by an 8 across the entire row for the red pills. And that represents the total amount of units of each of those vitamins that she'd be getting from the red pills. Alright, and then the same thing with blue. She's taking Y pills, I don't know how many, but I'd be multiplying all of those units, maybe doubling or tripling, depending on how many pills she takes. Now if you set up this chart, the work is almost done for you, and my suggestion will always be put your variables, give them each a row, and then if there's anything else in terms of other quantities that relate to those variables, then give those columns. Right? And now looking at this, if you look at each column, those give you the constraints for each of those vitamins. So I can say that 8 units of vitamin A coming from the red pills plus the 2 units of vitamin A coming from her Y pills have to be at least 16 units. So I'm just reading down the column. And then from column 2, I can say that the 1 unit of B1 from the red pills and the 1 unit of B1 from the blue pills must be at least 5 units per day. And then finally for C, 2 units from red and 7 units from blue must be at least 20 units. And there are my 3 constraints that are in the problem, and then I also just need to add in the 2 understood ones that she can't take or purchase any more than or any fewer than 0 pills. Right, so there are all of my constraints. Alright, and then next I need to describe the steps taken to graph the feasible region. So I'll go through the process of graphing, and then you can describe in your own words or submit an image of your graph instead, instead of describing each step. Okay, so for the first inequality, 8x plus 2y is greater than or equal to 16. Let's go through both ways that you could graph this. So first of all, if I wanted to graph this using the slope and the intercept, I would look at the boundary line when 8x plus 2y equals 16, and if I subtract 8x from both sides, I get 2y equals negative 8x plus 16, and then dividing both sides by 2, I have y equals negative 4x plus 8. Alright, so one option would be to plot the intercept of 8, and I'll just do a scale of 1 here. Okay, so there's my intercept of 8. Alright, and then a slope of negative 4, so down 4 and to the right 1. And I'll go once more down 4 to the right 1. Alright, and then draw a line through those points. And notice I still am dealing only with inequalities which are greater than or equal to, or less than or equal to, so all of these are going to be solid lines. Alright, so there's my line, and then for this inequality I should be shading above that line. Alright, since 0, 0 makes the original inequality false. Right. Now notice another option. I could have also chosen 2 points that would make this equation true, and it looks like the intercepts would work nicely here. If I let x be equal to 0, then I can see that 2y is 16, and so y must be 8, so I have the point 0, 8, which is just the intercept point that I've already graphed. And then if I let y equal 0, I can solve for x. So then I'd have 8x equals 16, and I see that x must equal 2. So I have the point 2, 0, which is in fact the other point that I did graph on that line. Okay, so two different ways to graph that inequality. Alright, moving on to the next one. Alright, x plus y is greater than or equal to 5. Alright, this one might be nice to just choose some points. So notice the points 5, 0, let's see, 4, 1, 3, 2, 2, 3. Anything that adds up to 5 would work in this case. And you can take your pick which of these you like the best. Alright, we just need 2. Alright, so I'll choose, I tend to like intercepts, so I'll choose 5, 0. That's here. And 0, 5. Alright, and it looks like 1, 4 is also another point that's going to intercept with the line that I already have, so that's good as well. Oops. Okay, and then I'll just draw the line through those points. And let's see if I can get this any closer. Okay, I think that looks pretty good. Alright, and for shading, x plus y has to be greater than or equal to 5, so 0, 0 will not make that true, so I need to shade above that line as well. Alright, and then my third inequality, 2x plus 7y, and we'll do equals 20, try to graph the boundary line. I can see that the point 10, 0 will work. And then if I try to let y be 0, or I'm sorry, if I let x be 0, 20 isn't evenly divisible by 7, so I don't really like that one. If I look at maybe multiples of 7 instead, I know 2 7s is 14. I'd need 6 more to get to 20. So if I let x be a 3, that should work. Alright, so 2 times 3 is 6, 7 times 2 is 14, 6 and 14 is 20, that does work. Alright, so you might want to just look for numbers that work nicely, and so that you don't have to deal with fractions or decimals. Alright, so those points would be 10, 0, 6, 7, 8, 9, 10, 0 is here, and then 3, 2 is here, and looks like I have another intercept where that hits my line, so that's nice. And I'll try to get a nice even line through those points. Okay, close enough. Alright, and again, if I looked at the original inequality, I think 0, 0 will make this false again, so I will need to shade above that line as well. Alright, so this is where the example looks a little different than your other two graphs in examples 1 and 2. It turns out that the region of feasible solutions is actually what we would call unbounded. And you can see that there's no upper restriction in any of these constraints. We've talked about that she needs at least certain amounts of vitamins A, B1, and C, but there is no maximum of the amount of vitamins that she can take. Right? Now, it kind of makes sense. There's sort of an understood constraint. A person might be able to take 10 or 20 pills in a day, maybe even 100, but it honestly would not be possible for someone to take, say, 1,000,000 pills in a day. All right? So if you try to graph this feasible region, you're going to end up graphing above all three of those purple lines, and it's going to look something like this. And you really can't shade the whole thing or even identify all of the vertices because some of them are just too large. All right, so we've got 4 of them. We've got the bottom 4. We've got here, 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 and here. But then your other ones would be way out at infinity, kind of in that direction. All right, so if you want to think of it as just unbounded or as having sort of an implied constraint that we just can't see, that somewhere up there it's below a very large amount of pills. Now this would be a problem if we were trying to maximize something, because we would need to check those vertices that are not graphed, but in this case we're trying to minimize a cost, so we can fairly certainly rule out those vertices as being our solutions, because it makes sense that the more pills you purchase, the greater your cost will be. So we really are mostly interested in just the small number of pills that can be purchased while still lying above those lines to indicate that she's getting enough vitamins. Alright, so all of that to say, you may want to discuss what this region would look like, but you won't really be able to box in or draw the entire region, nor will you be able to identify all of the vertices, just the finite ones. So it looks like we have 4 of those. We have 0, 8, we have 1, 4, we have 3, 2, and 10, 0. Okay, so those are the ones that we'll test, and let's make a chart of values again. So we have different values for x and y, and then we have our cost function this time, our objective function, and that was 10 cents per red pill and 20 cents for blue pill. Alright, so we'll list the vertices, and we will test all of these in the objective function. Alright, and you can go ahead and do all of this math. So when she purchases 0 red pills and 8 blue pills, that's a cost of 160 cents. 1 red and 4 blue is 10 cents plus 80 cents, or 90 cents. 3 red and 2 blue is 30 cents and 40 cents, or 70 cents. And finally 10 red and 0 blue is 100 cents, or $1. Alright, so it looks like we do have a minimum out of these 4. Okay, the 0.32 giving us a minimum cost of 70 cents. Alright, so 3 red pills, 2 blue pills. Alright, and the minimum cost would be 70 cents. And that's it for example 3.